Hello friends, so this is the second part of aliphatic nucleophilic substitution, and here we will be talking about the main two types of reaction. The first one is SN1 and the second one is SN2, and also we will talk about their another version, that is SN1 prime of SN1 and another version of SN2 which is SN2 prime. So nucleophilic substitution reaction, it involves displacement of a nucleophile by another. So from this general example, you can see that Rx, just imagine for some time that if this Rx bond is broken, then it is X minus. So X minus, it is replaced by Y minus. So that is why our new product is Ry and X minus. So it is a displacement of one nucleophile by another nucleophile. Here it is written Lewis base, though you can also call it nucleophile. Lewis base also can be called because there is some electron density over Y. Now aliphatic substitution reaction, there are two main mechanisms. The first one is SN1 and the second one is SN2. So here S stands for substitution in both cases, N stands for nucleophilic, and 1 and 2, this number represent the kinetic order of the reaction. So kinetic order of the reaction means the exponent of the concentration term of the species which is involved in rate expression. Now for the reaction to occur in homogeneous solution, the solvent should be such that can dissolve both our substrate, in this case Rx and Y. So both the substrates should be soluble. But the problem is Rx, which is the alkyl halide, it is soluble in organic solvent. It is not soluble in water. On the other hand, nucleophile, that is Y minus, it is soluble in, not in organic solvent but in water, because mostly it is salts. Suppose our nucleophile is MeO minus, that is sodium salt of MeO minus, sodium methoxide. So in that case obviously it will not be soluble in organic solvent. So our one substrate, that is our main substrate, it is soluble in organic solvent, not water, but Y minus, it is not soluble in organic solvent. So what we can do under this condition? One way is we can use mixed solvent, that is a solvent, mixture of solvent, alcohol plus water. And another way is that some solvents can dissolve both the substrate and the nucleophile. So that is another thing that we can do. It can dissolve both the nucleophile and the alkyl halides. And for example, DMSO, dimethyl sulfoxide, and DMF. So these are the two ways that we can follow to avoid this type of problem. Now we have some examples of nucleophilic aliphatic substitution reaction. In the first step, you can see that our substrate is alkyl iodide. So alkyl iodide and our nucleophile is HO minus. In the second case also, substrate is same, but now our nucleophile is neutral. So in the first case, product is neutral, leaving group is anionic. In the second case, as our nucleophile is neutral, so obviously our product will be positively charged because nitrogen it has total 4 bonds, and leaving group same as before. Type 3, that is now our substrate is positively charged species and nucleophile is HO minus. And in the fourth case, our substrate is same, but now the nucleophile is neutral. So obviously our product is, because sulfur is attached to 3 atoms, so that is why sulfur is positively charged. In both cases, nucleophile, they are same. So type 1, 2, 3, 4, first case, substrate neutral, nucleophile is anionic. Second case, substrate neutral, nucleophile is also neutral, and leaving group and product both are, there is some charge. Type 3, substrate is positively charged, nucleophile is also negatively charged. Our product, leaving group, both are neutral. And the fourth case, substrate is positively charged, nucleophile is neutral, product is positively charged, and leaving group is neutral. So different possibilities may be there. Now come to the unimolecular SN1 reaction. Why we are calling it unimolecular? Because only one substrate is involved. So that is why we are using it here 1. So it is unimolecular. If it is 2, then it will be bimolecular. Now, though it is unimolecular, but there are 2 steps. Unimolecular because only one species is involved in rate expression. So rate of the reaction, it is rate constant into the concentration of the species Rx, that is alkyl halide. So this is our first step. In the first step, this Rx bond will be broken and we are getting carbocation and X minus. Now when Rx dissociates, we are getting carbocation intermediate and X is leaving group. Now this is the first step and this step is slow step. So this is the rate determining step, and you can also see we have used equilibrium sign. So this is reversible step. And the second step, now again there is the carbocation. Now nucleophile comes into picture. It is attacking R plus and it is forming the product RNU. So here carbocation and the nucleophile both are combining with each other. Here the sign is single arrow. So it is not, there is no equilibrium. So this is irreversible and this is first step. So the overall reaction, if you just add these 2 reactions, overall reaction we get this one. But as in our slow step, that is the first step, only Rx is involved. So in the rate expression, we have only the concentration term of Rx. There is no concentration term of nucleophile. That is why it is unimolecular reaction. Now here in the second box, the same substrate Rx, you can write it in detail. So now here's R, it is written as CR3. So CX bond, again it is broken. So this is the slow step. So this is our carbocation. Now the carbocation intermediate, the nucleophile can attack from both sides. So we are getting 2 types of product. So if the amount of these 2 types of product, suppose A and B, though they are same product, but they are depending on the chiral center, that is whether it is R or S, these 2 are enantiomer to each other. So there will be racemization if A and B, they are forming 1:1, that is 50%, 50%. And that is possible only when your carbocation, its lifetime is very high. But suppose for some time this CX bond is broken and X, it is weakly attached with the C plus. So in that case, nucleophile, the chance is very high that nucleophile, it will attack from this side more. So in that case, the B product, it will be formed more. Suppose B is 60%, A is 40%. So depending on the lifetime of the carbocation, if it is very high, then there is a high chance that AB will be formed in 1:1 ratio. That is, the amount of both A and B are same. But if it is not the case, then if X is, suppose CX bond, it is breaking in a slow manner, then X still will be weakly attached to C plus, and as a result, the chance will be high that nucleophile will attack from the opposite side. Fine. So carbocation stability here is very important. That is 3 degree, then 2 degree, and then 1 degree. So carbocation stability, as we know, the tertiary carbocations are more stable. So that is why SN1 reaction rate, it is very high for tertiary halides. After tertiary halide, the rate of the reaction, it will be maximum for 2 degree. And see, for 1 degree there is a cross sign. So that means it is almost impossible for primary halide to take part in SN1 reaction. Polar protic solvents such as ethanol, methanol, etc., they support carbocation formation because they stabilize the intermediate carbocation. Now the role of polar protic solvent, why it is used in SN1, that will be discussed in detail in next video. Just remember for the time now that polar protic solvents are used in SN1, and aprotic solvents, they do not support the carbocation formation, so they are not used for SN1 reaction. Now here weak nucleophile is okay. Why it is so? In the rate expression, if you look carefully, there is no concentration term of your nucleophile. So it doesn't matter whether you have taken good nucleophile or bad nucleophile. So that is why it is written that weak nucleophile is fine if you have taken. Fine. Next is bimolecular, because now we can see bimolecular too. Why? Look at the rate expression. There is concentration term of Rx, that is our alkyl halides, our main substrate, and the concentration of nucleophile as well. So that is why it is bimolecular reaction. So that is why it is bimolecular reaction. This is a single step reaction, though it is written for our convenience in 2 steps, but actually this is a single step. This species is actually transition state. It is not intermediate. We use this type of sign for transition state. So this transition state we have written again in the second equation. Actually this is not second step, this is a single step reaction. Now the Rx bond will be broken fully and NUR bond will be formed fully. But in the transition state, what is the difference with the actual product? The difference is here the bond between nucleophile and R, it is just forming. So that is why there is partial positive charge over nucleophile, because it is giving electron towards R. And the bond between R and X, it is just breaking. So that is why there is negative charge over X. Fine. So there is a single step. So as this is a single step, so obviously this will be the RDS step. And it entails 2 species. So that is why it is bimolecular. Now the Rx, it is written as CH3X. CH3X, methyl halide. So nucleophile, it is attacking the carbon which is carrying the leaving group, that is X. So this is our transition state which is penta-coordinated. Here you can see the nucleophile and carbon, the bond between these two, it is just forming and this bond is just breaking. So this is our final product. So in this case we will mostly see inversion. Why it is so? Because the bond formation between nucleophile and carbon and the bond breaking between carbon and X, it is happening simultaneously. So that is the reason the nucleophile, it is always approached from the opposite side of X. Here steric factors are important, because unlike SN1, where you can see where the nucleophile is attacking, this is tria-coordinated. That is, when the nucleophile is attacking, it is tria-coordinated species. But here it is penta-coordinated species. So obviously we have to consider the steric factor. So as steric factor is important, 1 degree halide, it will be having the maximum reaction rate, then 2 degree, and for 3 degree there is a cross sign. So mostly it doesn't take part in SN2 reaction. Now here, or in the example, the substrate is CH3X, which is not actually 1 degree. So 1 degree, if it is 1 degree, you can take the example of suppose CH3, CH2X. So if it is simply methyl halide, then that will show the maximum rate, then 1 degree, then 2 degree, and 3 degree it is almost reaction rate is nil. Polar aprotic solvents such as acetone used in case of SN2. You have seen in case of SN1 it is polar protic solvent, but now it is polar aprotic solvent. So aprotic solvent destabilizes nucleophile. That means it increases its reactivity, and it is required in this case. Why it is so? Because if you look at the rate expression, their concentration of nucleophile is already mentioned in the rate expression. So obviously our nucleophile, it should be very reactive. But if you are using protic solvent, it will stabilize the nucleophile. As a result, its reactivity will decrease. But if you use aprotic solvent, then it will destabilize the nucleophile. As a result, reactivity of nucleophile will increase. And the third point is strong nucleophile is necessary. Now strong nucleophile, obviously it is necessary because in the rate expression the concentration term is involved. So now it matters, unlike SN1, whether you have taken good nucleophile or bad nucleophile. So if you have to take good nucleophile always in case of SN2, because it is involved, its concentration term is involved in the rate expression. Now, for the nature of living group, it is important for both SN1 and SN2. Why? Because in the rate expression, the concentration of the Rx in which the living group is involved, X is our living group. So Rx, it is always involved in the rate expression, whether it is SN1 or SN2. So that is why the nature of the living group is important in both the type of mechanism. And here we have one simple example, I minus having more that is better living group than Br minus, and then which is better living group than Cl minus. Now we will see both the mechanism simultaneously so that you can compare SN1 and SN2. What is the main difference here? So this is the first step, which is very slow, and this is reversible step, and the second step, which is fast. Now there are two arrows depending on the nucleophile, whether it is attacking from left hand side or right hand side, because this species is planar and this is intermediate, not transition state. So depending on nucleophile, it is attacking on which side, we can get either this species or this species. And for SN2 reaction, though there are two arrows written, but it is actually a single step reaction. Single step. Directly you are getting the product, because it is nothing but transition state. It is not intermediate. Okay. So in the transition state, the bond between nucleophile and C, it is just forming, and the bond between carbon and living group, it is just breaking. So this is penta-coordinated, and our final product, the nucleophile, obviously it is always attack from the opposite side of our living group. Okay. So that is why we will get most of the time inversion in case of SN2. Now the energy profile diagram of SN1 and SN2. Obviously the first picture, it is for SN1, because here you can see there are two hump. So the first hump, it is the transition state 1, and the second hump, it is the transition state 2. So the first hump, that is the transition state 1, here you can see this arrow, this energy gap between the starting material, that is our substrate alkyl halide, and the transition state. This energy gap, it is known as activation energy. So this is the corresponding energy in the y-axis, you can see here. So this point, it is the energy of our starting material, and if you draw a line here, this is the energy of the transition state 1. Now this activation energy, which is the activation energy of the second step. Now this is our intermediate carbocation. Intermediate, I am writing here INT. So here you can see, if you consider this intermediate at the starting material for the second step, and this is your transition state 2, so this energy gap, it will be second activation energy. As we know, the first step, it is the slow steps. Obviously del E1, its value will be higher than del E2. Okay, so that is why the second step, it is the first step. And this energy gap, this is energy gap between the starting material and the reactant. Sorry, starting material and the product. So this is our product. Now come to SN2. This is SN1. So here we have a single hump and we have a single activation energy, because this is our only transition state and there are no intermediate involved. Here our starting material is methyl chloride, nucleophile is HO minus, and final product is methanol, and living group is Cl minus. Okay. Now come to another version of SN1, which is known as SN1 prime. So when it is SN1 prime, what is the difference with SN1? Now your substrate is allylic halide, that is allylic substrate. So here we have taken MECH double bond CH, CH2OH. In the first step we are using HBr. Now actual nucleophile is Br minus. After some time you will see the mechanism, it will be clear. So see, when simply the place of OH minus it is taken by Br, we are calling it SN1 product. That is very normal, that we have just seen. But there is another possibility. See, now the Br, that is the incoming nucleophile, it is attached to this carbon, not the carbon with which the original OH, that is the living group, is attached. So this is our SN1 prime product. So how we are getting SN1 product, that is very clear to us. But how we are getting SN1 prime product? For that you have to look at the mechanism. So first, in presence of HBr, OH will be protonated. So there is a positive charge over oxygen. Now this OH2 will be removed, that is minus H2O. So when H2O is removed, then there is a carbocation formed. This is our carbocation. Now this double bond between two carbon, it can be shifted to the next two carbon. So that is why now the double bond is between these two carbon, and this carbon is now electron deficient, carrying positive charge. So if under this condition Br minus is attacking this positively charged carbon, then you will get this SN1 product. But if Br minus is attacking here, that is after conjugation, the new carbocation that is generated, if Br minus is attacking the new carbocation, then you will be getting SN1 prime product. So that is the difference between SN1 and SN1 prime. This is very simple. Now come to SN2 prime. Now when it will happen? Again we have taken allylic halide. When steric factors prevent normal SN2 attack at an allylic carbon. Now how the steric factor is preventing normal SN2 attack here? You can see the Cl, that is a leaving group, it is attached to gamma carbon, and there are two methyl groups attached. So this, to reach the nucleophile, to reach this gamma carbon, it is not very easy because of the steric hindrance. So here our nucleophile is PHS, that is our nucleophile, and sodium salt is involved. So this is a sodium salt of PHSH. So simply take PHS minus as the nucleophile. So it is attacking not the carbon with which directly leaving group attached, but it is attacking the alpha carbon. So now the CC, the double bond between C alpha and C beta, it is shifted to the two carbon, that is carbon, gamma carbon and beta carbon, and chlorine is leaving. So after removal of chlorine, the new product that we are getting, that is SPH attached to alpha carbon. So this is our alpha carbon. It is not attached to the gamma carbon, that is originally the Cl leaving group, it is attached to the gamma carbon. But in the product of SN2 prime, this is SN2 prime product, not SN2 product. So if it is SN2 product, then your SPH should be attached to gamma carbon only. But your SPH is attached to alpha carbon. Okay, so this is a SN2 prime product. Another example. So in this example, this is cyclobutene, 4 carbon ring. There is a double bond also. So this is also, see this leaving group, it is in allylic position. So Mu minus, which is our nucleophile, if it is attacking directly this carbon, that is the leaving group bearing carbon, or this carbon, because both the carbons are equivalent. There are chlorine and deuterium attached. In this case also chlorine and deuterium attached. So if the nucleophile, it is attacking directly this carbon, then you will get SN2, normal SN2 product. But the nucleophile is attacking here. The double bond, it will be shifted in this position and leaving group will be removed. So this is our final product, that is SN2 prime product. Okay, so that is all about SN2 prime. So if you find this video helpful, please like, share and subscribe, and thank you for your time.